things. So introduction. If these slide decks get shared, there's a bit about myself and who Geo-Energy are. We were basically established in 2020. There was a hole in the market for designers, so pulled together a team of 9 designers. Between us, we've got over 75 years worth of experience. And we're in quite a unique position because over the last 20 years, we have installed, we've designed, installed, commissioned, optimized, operated, and fault found on over 400 megawatts worth of predominantly ground source heat pump installations in the UK, with a few overseas. So I don't really want to take people back to school, but I just want to go back to a couple of basics and pick up on them, and then explain why that enables us to look for opportunity out there. So physics, Boyle's law and Charles' law, is something we learned at O-level for some of us, or GCSE for the younger ones, at about the age of 15 at school. So P1 V1 over T1 equals P2 V2 over T2. In layman's terms, if you compress the same volume of gas, the byproduct is heat. It was Lord Kelvin that first proposed a practical heat pump system in 1852 as a heat multiplier as well as a refrigerant. If we look at the heat pump cycle here, very simplistic. We have an evaporator which absorbs energy, and the typical refrigerants that we use, anything over minus 20 degrees centigrade is useful heat. So just bear that in mind when you're looking around you at what's around sources of waste heat. Heat can be hotter than minus 20. Compressor compresses that. Again, we've got great moves in refrigerants, and we can now get temperatures of up to 150 degrees centigrade. 120 is quite normal, and heat pumps will produce steam. Then the circuit continues. We go through an expansion valve, very much like an aerosol, where we go from a compressed liquid back into a very cold gas. Now, the coefficient of performance of a heat pump is the electricity into that compressor generating your heat out. So why is that good? So with a heat pump, 1 kilowatt of electricity can absorb so many kilowatts of naturally occurring heat. And this can be in any form of open loop, closed loop, energy piles, ponds, lakes, horizontal ground collectors. There are numerous ways of absorbing that energy into a water source or a ground source system. So typical heat sources are rivers, canals, bodies of waters, ground arrays, which can be horizontal in fields and things, sewage system heat recovery in both what I would term as the lumpy side of sewage and the cleaner post-treatment works. And then you've got heat rejection from things like chillers, data centers, CHP, solar thermal, exhaust air ventilation, process cooling, and process water discharge. All of these are above minus 20 and therefore useful heat. The warmer they are, the more efficient the system. Generally, a 1 degree rise in source temperature equates to about 2.5% increase in efficiency. So how do they heat? They absorb cold, we put electricity in, we compress that low-grade heat, we generate a high-grade heat. So how do they heat and cool at the same time? Well, if we look at a heat pump, traditionally a chiller, they're again traditionally air-cooled, they're absorbing energy from a refrigerator, and the byproduct of that is heat. So if we can put this heat pump in a situation where it is heating and cooling at the same time, suddenly our coefficient of performance of heating of 4 and COP of 3 for cooling with 1 kilowatt of electricity can generate 7 kilowatts of heat. And that's termed as 700% efficient. Now that's applicable when you're joining perhaps a data center with heating buildings, or indeed if you're looking at a mixed-use building, you might have, take a Sainsbury's supermarket. In winter, they're trying to heat the space and they're also trying to chill their food. So what makes a heat pump low carbon? There's a very good app, if you don't know it, it's called Grid Carbon. This monitors, it's run by Oxford University, and it monitors the various generation assets on the grid and gives you an average of the grid carbon. I had a quick look the other day, and there were 84 grams of CO2 per kilowatt hour of electricity, and wind were very dominant on the system. And then if you turn your phone sideways, you get a graph and it tracks it per hour, and it shows you in a color ways how that generation is made up. So if we go back about 10 years, the grid had a greater carbon intensity than natural gas. The grid was around 400 grams of CO2 per kilowatt hour, and natural gas was around 330. Now there's been huge investment in PV, in wind, nuclear, but it's taking time to come online, hydro, interconnectors. So we have decarbonised our grid hugely. When I had a quick look this morning with a bit of wind, it was sitting at around 140 grams of CO2 per kilowatt hour. So if you put that electricity into a heat pump, you're on the left here, it shows you if you have a coefficient of performance of a heat pump of 3.2 for a ground source heat pump. In England this morning, electricity, the grid was 169 grams of CO2. Your heat pump would be generating 42 grams of CO2 per kilowatt hour, and versus a gas boiler at 215, oil boiler at 320, or coal at 630. The graph here shows you the decarbonisation of the grid since 1950, from when electricity was predominantly generated with coal, and now we're down at below 200 with a mix of renewables and gas for peaking. This chart here shows you the different types of heating technology. So we've got the light blue, which is direct electric, which will come down proportionally to the decarbonisation of the grid. You've got a gas boiler, which stays pretty even, but now that we are bleeding green gas from AD into the grid, that is being decarbonised very slightly. We've got CHPs, which are now becoming seen as more polluting. And then we've got heat pumps. So as the grid carbon comes down, so that lower green line shows a much greater decarbonisation. And with heat pumps at point of use, there are zero emissions. So here's some ground source heating and cooling project examples. So this was Oxford University have invested quite heavily in ground source. The Royal Observatory Quarter has a number of buildings. It started with Earth Sciences, then moved into maths, and now we have Blavatnik School of Governance, and then we go beyond that, and there is Beecroft, which is the physics laboratories. Currently at Beecroft, they are laboratories for doing world-leading physics research and development. We're getting COPs in excess of 5 there because we are managing to harness both the heating and cooling aspects of the heat pump. Orkney Schools, surrounded by wind, SSE had an aspiration in around 2010 to decarbonise the schools and public buildings there. So installed heat pumps with the view to run them off zero carbon wind. Mansfield Hospital at the time, which was in around 2012, I think, was the largest lake loop system at 10.4 megawatts of heating and cooling. The heat pumps are the sole source of cooling for that hospital. They do a huge proportion of the heating, but there is also gas boiler backup. And that consisted of slim jims is what they're called, basically stainless steel radiators sunk into the lake, and we absorb energy out of that lake. London sits on a huge chalk aquifer, and there's an opportunity there to drill down into the aquifer. It's around 60 odd meters, depending on where you are, and extract that water and use it through a heat exchanger to heat a heat pump. And there's a whole list of jobs that were done in the last 10 years within London using open loop. Open loop from the Thames, Dave's talked a bit about this, but here's a system in the Thames, which is tidal. There's a floating pontoon. The river extraction point filters are hung underneath that pontoon, so they're always within the water there. A lot of myths out there about how heat pumps don't work in old buildings. So here's some examples of buildings where people don't think heat pumps will work. This is Downing College, Cambridge, listed building. Heat pumps were drilled into, boreholes were drilled into the quad, and we used ground source heat pumps to heat that building through the existing system. Decarbonising the past as well as the future. Here we have a church which was built around the 10th century. About 5 years ago, we retrofitted a heat pump and took an opportunity to put underfloor heating in there. So we're going back to harvesting low-grade heat from the ground and using what the Romans did in a building that's approximately 1,000 years old. Church of England are adopting heat pumps. They have a strategy to decarbonise by 2035. Landmark Trust have a very interesting, quirky estate A lot of theirs are remote and on oil, and they are looking at heat pumps decarbonising. We've got Historic England and the National Trust. All these organisations recognise the preservation temperatures that heat pumps offer and the opportunities they give to these old buildings. So they maintain the temperature in there. They work by either convective or radiant heat, and they ensure that the fabric of the building and the artifacts in there are kept above 16 degrees C, 15.8 being the dew point in water, which is when you start to get moisture and mildew forming on things. So what is the heat network? Basically a centralized heat generator and distributing that high-grade heat out to a mixture of buildings and premises. And also chilled water can be sent out too for doing heating and cooling. Talk about cogeneration. Conventional power generation, you burn to fuel to generate power through a steam turbine. Our thermal plants, which we don't have many left in operation, 67% of that energy was wasted and blown into the atmosphere through the cooling towers, and only 33% went to the generation of electricity. Cogeneration uses, we use the heat is useful, and we have direct drive onto turbines for generating electricity. They are more like 80% efficient, only losing 20%. So a typical heat network using fossil fuels is called a third generation. If we move to a heat network using a mixture of fossil fuels and renewables, we call that a fourth generation heat network. So we look at the CHP equation here, and the 20% that's being lost is exhaust losses, intercooler heat rejection, and heat losses from the casing of the system. So if we can harness that and use it in the low-grade side of a heat pump, suddenly we're making not only the CHP more efficient, but we're generating a warmth for the ground source heat pump. So here we can use waste heat from the flue losses, intercoolers, surplus heat. We can store that in boreholes or energy piles in the ground and use it in the opposing season for the ground source heat pump. And there are more and more people looking at this now, how to make the best use of a CHP. Generally, they're used for electrical generation, and the heat gets wasted. So this is an example of an integrated energy centre at Old Oak Common. This was the Crossrail service sheds for the Crossrail trains doing the east-west routes in London. There are 25 150-metre deep boreholes. There are 466 15-metre deep energy piles. It provides 936 kilowatt thermal of heating and cooling. We've got CHPs in there generating all the electricity. There's 220 meters squared of solar thermal on the roof going into the boreholes and directly into the heating system. And there's nearly 1,500 square meters of solar PV on the roof there. Crossrail, when they built this, took a 120-year view on the asset in the ground. And this is quite an important thing. Once you've installed that ground collector or your river extraction system, that's potentially up to 60% of the capital of a ground source heat pump. But if that has a lifespan of 120 years, then what you're then looking at is the cost of the heat pump, or the return on the heat pump is just that 40% that's left to buy the capital of the heat pump, which are the sort of the serviceable parts that need replacing. Caird Park in Dundee is a fourth generation heat network, a mixture of ground source, CHP, gas boilers, boreholes, heating primarily the centre of excellence for sport, but adding on over time additional buildings. Examples of ground source heat pumps in heating, cooling and rail infrastructure. A lot of the oversight development in London on Crossrail uses the infrastructure that's put in the diaphragm walls and the grout shafts below the ground when Crossrail is being constructed. And the high-speed rail system in Spain's inner plateau also has a cooling system which is derived from ground source. Talking about waste heat from sewage, this is final effluent discharge to river, which is effectively clean. A city has a huge amount of this, and in this case, there's 72.5 megawatts worth of waste heat captured, fed into heat pumps, which in these instances was used to heat glass houses. So there's 6 times more shard there, more glass there than the shard. collect all the rainwater off the roof, so we can grow 10 times more yield within those glass houses using a low carbon technology and zero wastage. A great example of a circular economy. So in heat pumps, there's a huge importance in controls. If I go back 20 years, when people were starting to put heat pumps in system, you would find a heat pump company installer who would install the ground collector, free issue the heat pumps as boxes to the M&E contractor who would then install it. A lot of those systems really struggled to operate efficiently because no one had appreciation of the whole system and how it should all work together, not only the harvesting heat at one end, but the actual performance of the heat pump and how you deliver that at the other end and how you do it with sympathy for a heat pump and efficiently. So controls are probably the overall thing that brings a whole heat pump system together. So moving on to from fourth generation to fifth generation, what is a fifth generation heat network? Fundamentally, we're using an ambient heat loop. So this is energy from nature running at anywhere between 0 and 20 degrees centigrade from water, boreholes, waste heat being distributed to buildings in uninsulated pipe. And each building has its own heat pump. So Dave has spoken about the centralized heat pump delivering out high-grade heat. In this situation, we're looking at ambient heat, and a single network can offer both heating and cooling opportunities to individual buildings. And that network can run between 10 and 20 degrees. And buildings doing space heating can run at lower temperatures because they're trying to achieve 21 degrees C. But a process will have its own heat pump working a bit harder. So the whole network is not compromised for the sake of the worst performing building or the most energy hungry building. From fifth generation, we move into what is a shared ground loop. And there are companies like Kenza who are proposing this. Rendesco are doing funded systems where they fund the ground loop, and builders of houses or social housing associations can install the heat pumps, look after the heat pumps. Again, this asset in the ground has a 120-year lifespan. The heat pump in the building is a serviceable item. A ground source generally has a lifespan of around 25 plus years, compared to an air source at around 10 to 15 years, depending on its location. So what are the advantages of ground source heat pump and shared ground collectors or ambient heat loops? A ground source heat pump has a more consistent source temperature, starting at something like 14 degrees centigrade in the ground, depending on the ground collector design, and dropping to 5 C in peak winter. An air source heat pump is having to work hardest when the air is coldest, and that results in a higher peak electrical demand. And this is something that's been recognized in North America recently. Both Boston and New York have looked at their heating and cooling demands. Traditionally, all buildings have chillers. They have an electrical demand. They're trying to cool those buildings when it's very hot outside, consuming a lot of electricity. And they've recognized that if you swap from chillers and gas boilers to ground-coupled heat pumps, you will cut your cooling demand on electricity by 72%, and you'll cut your heating demand, if it were an air source heat pump, by between 20 and 40%. And that's purely because your ground source temperature or your ambient temperature is a lot more even, and you're not having to work those heat pumps as hard and therefore not consuming as much electricity. An air source heat pump has a lifespan of about 10 to 15 years. A ground source heat pump, 25 years plus. And as I keep saying, the ground collector, potentially 120 years. At certain times in an air source heat pump's operating envelope, so anywhere where with the air temperature is between, the ambient air is between 0 and plus 7 degrees degrees centigrade, the moisture in the air is freezing onto the evaporator. And most of our winter in this country spends its time in that temperature envelope. So once the coil has frosted up, you then need to absorb energy from the building or your process in order to melt that moisture and blow it off as steam. And if we look at domestic properties, that's typically happening for 10 minutes after every 30 minutes of operation. So the opportunities for cooling with ground coupling is it saves 50% of the energy and carbon. Ground source offers passive cooling from the ground loop. So depending on your process, if in winter you've taken your ground loop down to 5 degrees centigrade, and the design of your cooling system in spring when things start to warm up a bit can take 10 or 12 degrees centigrade, For the cost of running a circulation pump, you can circulate that fluid within the cool emitters for very little energy cost. The pitfalls: integration of heat pumps into a building is critical, not just the source side, but also load side. Do not rely on manufacturers design your system. They may understand their products, but they very rarely appreciate the whole process and the whole system. Do not rely on equipment manufacturers to commission their items in isolation. So heat pumps, circulation pumps, pressurization units, etc., because they're generally not joined together. Ensure one designer has responsibility for the overall system design that brings all the parts together. Allow for seasonal commissioning to optimize the system, especially in new build. The theoretical building is often very different to the final working building, and you cannot manage if you don't monitor. Logging and reporting are key to a continued reliable and efficient operation of the heat pump systems. Heat pumps are rewarding when they're looked after. And to quote Aristotle, the whole is greater than the sum of the parts. Before I finish here, a bit of food for thought. For space heating, we're trying to heat a space to 21 degrees centigrade. We don't need 85 degrees C to deliver that. It's inefficient. For domestic hot water, point of use is often restricted to 46 degrees centigrade. So why store it at 65 degrees centigrade? Challenge the Legionella guidelines and use periodic sterilization. For process, are your set point fossil fuel legacies? What primary temperatures do you really need? What waste heat opportunities are there? Can you deliver both heating and cooling? Waste heat, look around you. Anything over -20 is deemed as useful heat to a heat pump. The Ground Source Heat Pump Association publishes and feeds into a number of guides that are out there, published by CIBSE, Department of Energy. We've got CP1, CP2, the CIBSE TM51, and various DEC reports. Thank you very much.